Hi guys, this is Anna, along with Annie and Chris, and in our group we worked on number 3 for homework number 2, parts A and B. We'll start off with part A. It states that for any sequence A sub n of positive numbers, we want to prove that the limit infimum as n approaches infinity of this expression A sub n plus 1 over A sub n is less than or equal to the limit infimum as n approaches infinity of the nth root of A sub n. So let's get going with the proof. To start off, we are going to take this expression here and we are going to let the limit of that expression be equal to alpha. We are also going to let that alpha be greater than or equal to beta, making beta a very small number. Here we know that there exists an n, which is an element of the natural numbers, such that a lowercase n will be greater than n, again making a capital N some very small number as well. At this point we will take this expression. This will imply that this expression A sub n plus 1 over A sub n has to be greater than or equal to beta. If I take that and multiply both sides by A sub n, okay, so that's what I've done. I multiply both sides by A sub n, which will imply that A sub n plus 1 is greater than or equal to beta times A sub n. Again, algebraically, these will cancel out, so that's how that happened. We'll manipulate this expression a little bit further by implying that this lowercase n can be replaced by the uppercase n, since that lowercase n was greater, so we can make those numbers a little bit smaller, which are still natural numbers. So these represents numbers in a sequence. We can manipulate this even further by making each side just a little bit larger, which will imply that A sub n plus 2 is greater than or equal to beta times A sub n plus 1. And both of these will be greater than or equal to beta squared times A sub n, since beta again is a very small number, and squaring a very small number produces an even smaller number. Increasing each side by 1 once again implies the following expression here, and we can continue this to make a general statement, replacing these increasing integers of 1, 2, and 3 along with the exponents by the variable k. This will produce A sub n plus k is greater than or equal to beta to the kth power times A sub n. At this point, what I'm going to do is I'm going to let this lowercase n be equal to this expression here, n plus k, and taking that and manipulating it by subtracting capital N from both sides, this will imply that k is equal to n minus capital N. What I will do next is I will replace this n plus k with that lowercase n, and replace this k with the expression that we developed here. And this is what we will get. So again, A sub n, coming from this substitution, is greater than or equal to beta, instead of k, n minus capital N, still multiplying it by the A sub n here. Just move this down a little bit so we can see the rest. What we'll do next is take an nth root of both sides, which will imply this expression here. The nth root of A sub n is greater than or equal to the nth root of beta to the n minus n power times A sub n. At this point, what I want to do is manipulate this right-hand side a little further. We know from our algebra rules that when we subtract exponents, this implies division. So beta to the n minus n power can be rewritten as beta to the lowercase nth power over beta to the uppercase. Again, we did have the multiplication by A sub n, which will remain in the numerator. And if you take this part only, excuse me, nth root of beta to the nth power, that will simplify to just beta outside of the radical, producing this following expression. So beta times the nth root of a sub n over b to the nth power. Just to clean this up a little bit here, we'll take these two expressions and put them together to imply that the nth root of a sub n is greater than this manipulated version of beta times the nth root of a sub n over b to the nth power. We'll take this to the next slide since I ran out of room. Let me slide that up. So here it is, that same expression from the previous slide. What I'll do next now is I will take the limit infimum of both sides as n approaches infinity, of course, implying this expression here. Again, we want to leave this alone, manipulate this right hand side a little bit more. We do know from the previous course 511, and it's also stated in the book by Theorem 320 part B in the text. Take that back a little bit. I forgot to say that we can take this and we can rewrite this as a multiplication of two limit infimums, as you can see here. And again, now this part here, that's what I was referring to as the Theorem 320, which we also proved last semester. That stated that the limit infimum of the nth root of a sub n over b to the nth power is equal to 1. So what I can do now is take this 1 and replace it into this expression, which will look like this. In addition to this, beta is just a constant, a very small constant, but it is a constant, and any limit of a constant is the constant itself. So this whole right hand side will simplify to simply beta, implying that the limit infimum as n approaches infinity of the nth root of a sub n is greater than beta. Now, we do know that this is true for every beta which is less than alpha, since beta is arbitrarily close to alpha. Before I make the next statement, just want to clarify the confusion that I had with this particular problem, so we can look at this a little bit more visually. I'm going to let this expression here be an x to demonstrate that. And once again, let's start off by placing alpha somewhere on the number line. And we know that beta is less than alpha. That's stated right here. So we can place beta right to the left of alpha. And here we just stated that this expression, which is our x, is greater than beta. So I could potentially place x right here in between beta and alpha. But as we said, beta is an arbitrary small number, which is less than alpha. So I could also place beta here. But if I do that, then I would have to place x in between those again. So x would have to go here. Again, beta could get even closer to alpha, and so on and so on, which implies that x, again represented by this expression, will have to be greater than alpha. Again, b is just a very small number that is very, very arbitrarily close to alpha, so there's no room for x. At this point, we can now conclude, I hope you've been able to see that as I have, that since x is greater than alpha, alpha has to be less than or equal to the limit as infimum as n approaches infinity of the nth root of a sub n. Now, in the beginning of the proof, let me just remind you here, we let the limit infimum as n approaches infinity of a sub n plus 1 over a sub n be equal to alpha. So what I could do is I can take this alpha here and replace it with the limit infimum. So that's what I'm going to do here. We took out the alpha from the left hand side and we'll replace it with the expression that was set equal to alpha. And this concludes a proof. At this point, this is what we wanted to prove. Let's just write it as a final statement. Therefore, the limit infimum as n approaches infinity of a sub n plus 1 over a sub n is less than or equal to the limit infimum as n approaches infinity of the nth root of a sub n. This concludes part A, and I will do part B in the next video.